Что, я есть там? Got it. Yep. Tell me when to start.
Please start.
Okay. Do you see my presentation? Hear me? See me?
Yes, yes, yes.
Okay, good. How's the audio?
Okay.
Perfect.
1, 2, 3, 4. Okay. Should I start or should we wait? What's the
No, just start. Okay.
good? So the whole story is, for me, it all started because I don't like complicated things, and I try to make them simpler and more combinatorial. So somehow, at some moment, I got interested by invariants of three manifolds. And there, second, oops, it doesn't work for me. Okay, anyway, I'll just go like that. And I started to learn something about quantum Chern-Simons theory, and it just too complicated for me, and there are these path integrals which mathematically are not well defined. So I started to think about some simple or simpler encodings of three manifolds, and in particular, somehow by chance got into some encodings of three manifolds just by planar graphs with certain weights on the edges and on the vertices. Wait, maybe I can really make it larger. Just a second. How's this? Still see me?
It was better before.
Yeah, it was a
Was
bit
better
yeah.
before?
No. Now it's a bit better.
So what? This is 1. This is 2.
Yeah, the two is good. Yeah.
Okay. All right. So I'll stick to that. Anyway, so I am going to explain first the motivation very briefly, and it will be a lot of hand waving. There will be nothing serious. It's just some very vague motivation. If you wish, then I'll switch to some simple encoding of three manifolds, and will tell you how, given a planar graph with certain weights, integer weights on edges and vertices, you can build a three manifold, and vice versa, why every three manifold can be encoded in this way. And maybe I will say a few words about these encodings, other encodings of three manifolds, and how to pass between them. But basically what I'm interested in, also I will briefly just say 1 or 2 words about some related objects, because that works also. You don't have to stick just to bare three manifold. It can be a three manifold with certain structure like spin or spin C structure, or you can work with links of three manifolds, or instead of just closed three manifolds, you can work with some mapping cylinders or elements of the mapping class group, etc. Now, as usual, such encoding will be non-unique, but I will describe some set of moves which suffice to relate any two graphs which encode the same three manifold. And in a funny way, this is related to electric networks and to some other things. So that's a cute part, actually. And then I'll discuss how, given this combinatorial presentation, you can construct some nice invariants of three manifolds, which are usually quite complicated. This perturbative Chern-Simons theory gives you some vague recipe for creating some perturbative invariants. How it can be done just purely elementary, in a way you can actually do given a pen and paper in a few minutes. So that will be the explanation how some complicated space configuration space integrals just in this language turn into some weighted counting of subgraphs. And then there will be a nice thing like generalized matrix tree theorem, but in a nice way, there will be some cycle rooted trees. Okay, so that's the point. Okay, how about this plan? Right, with you guys?
Я кратко переведу на русский язык. Все, что вы сейчас прослушали, можно пока считать, если вы что-то не знаете из этих слов, то это можете это пока проигнорировать. Самое интересное начнется через несколько минут.
Да. Как бы докладчик ничего еще не сказал. Okay, so there's some Chern-Simons theory, whatever it is, I'm not going to say. And it was just then presented as a certain way to explain the Jones polynomial in some topological or geometrical fashion. So, and Wheaton explained to mathematicians why the Jones polynomial and other topological quantum field theory invariants of knots and three manifolds have a certain geometric topologic interpretation in terms of something which they call quantum Chern-Simons theory. Again, I will not say anything about it, but anyway, it's some complicated physical theory which unfortunately also involves path integration. So it's not really rigorously well defined mathematically. There's a lot of questions there. What's the measure? How do you do that? In some simplest cases you can do, but in general it's very far from being rigorous. So mathematicians are very skeptical kind of to accept it as is. But it can be turned into some technique which is computable, and these are some Feynman diagrams, which kind of very combinatorial object. It's just a graph with certain data. And then all this perturbative Chern-Simons theory can be translated into something which is called configuration space integrals. And this is basically some construction when you, instead of just fixing one point in your manifold, you fix several, and for certain pairs of such points in your manifold, you look at some forms, and then you take a wedge of these forms and you integrate over some configuration spaces, and then you glue them together. You have to compactify, you have to blow up. There's a lot of technicalities involved. It is uncomputable, even in the simplest cases. The only case which I know where it was actually computed was for a round, flat unknot. You can also do something which is pseudo calculations. Just look at some properties of these configuration space integrals and say what do you expect for some simple knots, but this is it. It's not much than that. So it is extremely powerful. It contains all these universal finite type invariants, both of knots and three manifolds. It determines all of them, and it determines also all invariants which arise from quantum groups. So this theory is powerful, but it is extremely complicated technically. And if you don't know it, you shouldn't. So as I said, some explicit computations are almost impossible in this language, except for maybe one of the lowest degree invariant. This is. So instead, what we would like to do is to consider its combinatorial counterpart. So switch, instead of all these complicated stuff, into simple combinatorics. So we would like to take a three manifold or a bare three manifold, or with some structure, and possibly also with a link sitting in it. And you would look at it as a standard sphere, but somehow transformed in some very thin neighborhood of a certain graph. So I will explain how to do it and how, given a graph with certain decoration on it, you can make a surgery, a certain, whatever it is. It's just some kind of transformation of some trivial part of this sphere to obtain all closed three manifolds. So then what can you hope for? All your integrals which you do, they will be some integration over a huge part of your manifold, which is totally standard. It's just a three sphere. There's nothing interesting there, right? So we shouldn't expect anything non-trivial there, and something which would appear when your points in these configurations will all get into this very thin neighborhood of a graph. So in this sense, you can hope that these integrals will somehow concentrate in some smallish vicinity on this graph. So you can hope, if you're optimistic enough, that these integrals can be calculated into some discrete, with some discrete technique. So I would describe how hopefully there are these discrete Feynman diagrams, and then you will just, instead of integration, look at sums, and this will be, instead of integration, just a discrete sum over some subgraphs of your graph, which encodes the manifold. And so it's just a motivation, very vague motivation. It doesn't tell you anything, but there's certain hope to produce them. And this Chern-Simons theory hints on some types of these subgraphs which are suggested by it. And the graphs which you should look for are uni-trivalent graphs. If you work with links, and if you work with just pure closed three manifolds, these should be just trivalent graphs. And this is just a starting point. So it's an extremely vague idea, and we would like to turn it into reality. So there are obviously several steps we should do. So we should just define a suitable encoding of three manifolds and links by such graphs, and then find and also hopefully prove some corresponding formulas for link and three manifold invariants, which you obtained before by these configuration space integrals from the Chern-Simons theory. Okay?
Давай я прокомментирую. Слышно?
Yes.
Значит, о чем пока шла речь? Что трехмерное многообразие – это сложные топологические объекты, и нам нужно научиться двум вещам. Во-первых, нужно научиться их кодировать каким-то конечным способом, который с помощью каких-то дискретных объектов, графов, взвешенных графов, плоских графов. А во-вторых, научиться строить их инварианты таким же способом. Эти инварианты будут заключаться в том, чтобы подсчитывать какие-то подграфы, построенных графах или что-то в этом роде. При этом имеется сложная теория, которая называется теорией Черна-Саймонса, и которая, как объяснил Виттон, может служить руководящим направлением. Она подсказывает, как именно можно формировать эти инварианты, подсчитывая определенные подграфы в тех графах, которые мы рассматриваем. Окей.
Okay, good.
Yeah.
So, all right, so let's switch to that. Graphs, which will encode these three manifolds, which will, I will call them chainmail graphs, and I will explain why. You know what chainmail is? Кольчуга. То, что рыцари носили. Страшные, вот злые тевтонские рыцари, разгромленные доблестной российской армией много раз, там, да, все утонувшие. Вот они все, типа, носили кольчуги. Кольчуга соткана из маленьких тривиальных колечек, которые зацеплены друг с другом. So that's the kind of graphs I will look at. It will be a certain union. So these graphs will, for me, encode something which will be made afterwards from some little trivial standard circles somehow linked together. So I will now explain certain kind of notion what this graph is, and this word chainmail stands for its meaning. We will afterwards see that it is can be transformed into certain link made of some little trivial circles linked together. So that's why I call them chainmail graphs. So far, this word is just has no meaning. So it's a planar graph, and it should be decorated additionally with integer weights. First of all, each vertex is decorated by a weight, and I will call it D of a vertex V. And the vertex is balanced or nice or pleasant or whatever you call it if this weight is just 0. So this letter D stands for, you know, the first letter of the word defect. So I want to measure how far this vertex is from being balanced in some sense. So I will also call a graph balanced if all of its vertices are such. So if all vertices have a weight 0. In addition to vertices, also each edge is decorated by an integer weight, which I will call W for the first letter of the word weight. And there are certain agreements, very simple agreements about these. So first of all, a 0-weighted edge may be erased. So if a weight is 0-weighted, just erase it freely. And I actually can start not from a graph, but from what is called as what is known as a multigraph. So it has multiple edges which connect two vertices. But if you have two such edges which connect the same pair, you can just redraw them as one edge. So it's certain simple modification of a graph which is allowed, and you just add together their weights. And also you can look at loops, at looped edges, which start and end at the same vertex, and you can so far just erase them. So what I said so far can be summed up in these simple pictures. If you have two edges which connect the same two vertices and they have weights U and V, you can just exchange them for one edge connecting the same vertices with weight which is the sum. 0-weighted, 0-weighted edge can be erased. Looped edge with whatever its weight is can be also erased. Okay, any questions so far?
No, it's clear.
Your edges are oriented or not?
So far, not. Just as drawn. I can orient them if you wish, but there's no built-in orientation. So yeah, it's better actually to think that they have both orientations in some sense.
One comment. As far as I understand, you are talking about plane graphs rather than planar graphs. A planar graph is a graph that can be embedded in the plane. A plane graph.
Yes, okay, sorry. Yes, it is a plane graph. It's given together with its embedding into the plane.
Yeah.
It's actually is already in the plane. I look at it in the plane. It's with fixed embedding. Okay.
Right.
Good. Now, I will just announce for you already before that in this encoding, you shouldn't still know how do I do that and how do I construct a manifold from such a graph. But I just wanted to tell you that in many cases, it's extremely short and simple. For example, the sphere can be just given by this graph, which is a graph which has just one vertex and no edges. And the weight on the vertex can be plus or minus 1. I will discuss it afterwards. I fixed here -1, but it's good. It has certain 4-dimensional meaning. Product, another kind of very standard manifold, one of the best, which is the product of 2 spheres and the 1 sphere, can be encoded by equally simple graph, which again, it doesn't have any edges. It's just one vertex, but it's 0 weighted. So it's balanced. So for me, actually, the best manifold is S2 times S1 and not S3. In a funny way, that's kind of the basic and nicest object. Say the Poincare sphere, homology sphere, will be determined by just another graph, which is also in between the simplest ones. It just has one edge with 2 different endpoints. And this 2, 3, and 5, it's because of some reasons, and I will try to explain afterward. In some way which is hard to explain, but it already happened many times before. Some other simple manifolds have some more complicated description. For example, the 3 torus already needs this graph, kind of this rhombus type graph, and it's probably the simplest. I can draw several other graphs which will produce the same manifold, but it's one of the simplest. Sorry, I don't hear. What?
The question is whether you are able to encode in this way only orientable manifolds or not.
I never thought about non-orientable. This is pretty much the surgery, or if you wish, the standard technique for orientable manifold. I guess you can do also with some non-orientable, but I have no idea.
One more question.
I just never thought about it. It's probably a good question.
One more question. On the rightmost graph, there are vertices without weights, and also the
okay, yes. So
signs
yes. If there are no weights drawn on them, it means that the weight is 0. I just drop zeros. So it means that the vertex is balanced. So on this S2 times S1, for example, here, I should also drop this 0, but I just wanted to write it explicitly there. But in what follows, I will just drop these zeros in vertices. Okay. So
And
these are just few examples. You should not understand how it is done.
plus and minuses on the edges.
Plus and minus on the edges is +1 and -1.
Plus one and minus. Very good.
Okay. Just to shorten the notation. Good.
Good.
We okay? Want to translate? Okay, anyway.
No, it's okay. You may proceed. It's clear from the.
All right, so now I'm going to explain how actually, given such a graph, I want to produce a manifold. There are many ways to do that, but the simplest description uses what is known as a surgery on a framed link. Everybody know here what surgery on a link is?
I'm not quite sure that everybody knows, but let you.
Okay,
Yes.
so but first I will describe a link, and then we can discuss how is it done. Okay, so how do I? So given.
Sorry, каждому кольчужному графу сопоставляется некоторое зацепление в трехмерной сфере, как я понимаю, да?
Да.
И уже поэтому, точнее, не просто зацепление, а оснащенное зацепление. И поэтому оснащенному зацеплению делается хирургия, которая превращает трехмерную сферу в некоторое трехмерное многообразие.
Да. Такая двухступенчатая конструкция. So it's a two-step algorithm. The first one will be to produce a link, and this link will explain to you why this graph was called a chainmail, and then from this framed link, already you construct a three-manifold by the standard, well-known technique. So how do I construct a link? So first of all, given a vertex, I just kind of blow it up into a little circle, right? My graph lives in the plane, so this little circle will also be just a standard round little circle which lies in this plane. Now, when I have an edge which connects two vertices, right? So what I do with the vertex, I just blow it up, and it grows into a little circle. And then when I have an edge connecting two such vertices, I do the following. I connect these two circles just by straight ribbon, and then in the middle of this ribbon, I cut it, and I link these two sides of the ribbon together, as shown. And there are two ways to do it. There's positive and negative linking, if you wish. If you would orient your circles, all of them, in the same way, counterclockwise.
So you admit that your plane is oriented and
yes, the plane is oriented.
Oriented in a consistent way.
Yes. So then, if you're given an orientation of the plane, then you just orient all circles in the same way. For example, counterclockwise. But if you switch the orientation and orient all of them clockwise, nothing will change. Okay? The important thing is to orient them the same way.
But you need to do that simultaneously for all the edges, yeah?
Yes, for all edges. So I just explained to you what do I do on this positive edge, right? So there was this edge here in the picture. Do you see my mouse? Should I draw?
Yeah, we do see it.
So So see, my age was positive, or kind of it had +1 on it. So what I do is I connect these two little circles by a ribbon, cut it in the middle, and connect them, linking them by +1 linking. Okay. Now, what should I do if I would have -1 there? What do you think?
Значит, что нужно сделать, чтобы для минус единички? Если на ребре стоит минус единичка.
So I should just mirror this picture and do the negative linking instead of the positive one. So now what do I do if my age is 0 weighted? I just don't link them at all, right? Which means that I can actually kind of unlink this little piece. And that's why I can remove a 0 weighted age. Okay. Now, what would I do for an age if its weight is +7? I would add the same linking, but with coefficient +7. So this will look like a little Hopf link, generalized Hopf link with the linking number +7. Okay. So the weight on the age just describes for you precisely the way you link these two circles together. Okay.
Значит, если на ребре стоит +7, то мы должны две эти окружности зацепить друг за друга 7 раз в положительном направлении, где положительное направление такое, а отрицательное это ему зеркально симметрично.
Ну так, чтобы в процессе этого зацепления на каждую из двух окружностей не получилось узелка, правильно? Они остаются незауженными. Эти окружности, которые мы зацепляем друг с другом с коэффициентом зацепления 7, тем не менее, каждая по отдельности остается незауженной.
Да, каждая по себе это стандартная по-прежнему тривиальная окружность. Я собираюсь нарисовать зацепление, которое состоит из тривиальных круглых маленьких окружностей, которые немножко вытянуты вдоль этих ребер и там зацеплены вместе друг с другом. Поэтому я это и называю кольчугой, потому что каждое звено, оно тривиальное, это просто маленькая окружность, но они зацеплены друг с другом некоторым образом, таким простейшим.
Окей.
Я здесь нарисовал только +1, потому что если вы знаете правила, по которому складываются веса, и вы знаете, что 0 нужно стирать, вы из этого можете восстановить все остальные веса. Правильно?
Миш, скажи такую вещь. А если это +2, они
Да.
там такие, тогда там такие двойная косичка.
Да.
Но тогда у тебя они меняются местами после этого, правильно? Там
Нет,
эти...
ничего не меняется. Сейчас. Они же еще как-то хитро зацеплены. Сейчас я вам покажу, как это выглядит на следующей страничке. Давайте, вот сейчас где-нибудь. Вот, например, видите, как это выглядит. Посмотрите только на картинки пока. Не читайте текст, не смотрите на цифры.
Ну вот смотри,
посмотрите,
вот
как это выглядит.
Will you please speak English?
Okay, so just as an example, again, to explain what happens if you have, say, for example, linking number +2. Remember that one age with +2 weight is the same as two parallel ages with weight +1. So the moment I described for you what happens for an age with the weight +1, you actually do know what to do for +2, +3, +5, etc. And if you know that 0 can be erased, you also can guess what happens for -1. And you cannot just switch the places of these circles or something, because they are all linked in some complicated fashion in between them, because your graph is large, right? It's not just one edge, it's usually a lot of them. So here, let me just show you already now these pictures. How do you produce such links? Forget about these numbers, forget about these integer weights. Just look at the pictures. Right? So, for example, I start so far here from this Mercedes sign with 3 edges which are weighted by +1 and 2 -1s. So what So what I will get is a link which has 4 components. The number of components is the number of vertices. Each vertex corresponds to a component. Each component is trivial by itself. And they're linked in some kind of straightforward fashion. So think about them at this moment as all of them oriented in the same way, counterclockwise. And then the linking number in between these two is +1, in between these two -1, and in between these two also -1. Here is an example of what happens with your graph, which, as I said, describes the Poincare sphere. And it had one edge which was colored, weighted by +2. So instead of drawing one edge which is weighted by +2, I draw here 2 edges, as you see, which are just each one weighted by +1. And I do the same as I did before. And if you look at the picture, then you can easily see that it can be isotoped to this situation, which is this generalized Hopf link with a linking number +2. Okay.
Yeah, so that's actually was my question, because if we have, so there are 3 intersections here, basically, right? If there are 2, then we just it's just one line, right? Because it will go to the other side.
Yes.
And so you somehow want to imitate it by a different graph. So it's not this situation with this one edge.
What do you think?
Sorry. Not
I
sure
mean
what
that if we just take this this picture in the middle, and these lines 1 and 3, they
1 and 3, forget about them. As I said, just forget about these weights which stand on vertices. Forget about them.
I forgot. It's not a problem.
Okay, just don't look at it yet. I don't want you to look at it. It's forbidden.
Misha, if instead of this graph in the middle, when you have 2 vertices and one edge of weight 2 joining them, if you would have a edge of weight 3, what would be the picture?
Let me draw it. Just a second. Oops. Okay, here we go. Let me just draw it. So let me draw.
There will be 5 intersections of this sort. So it's always.
So if I look here, oops, why doesn't it work? Just a second.
Yeah, it should work.
It should, yes, but it didn't.
No,
It's some kind of these little games. Just a second. Let's try again. Here I go. So here's my edge, one edge of weight 3. Okay. So what I do then is I have here 2 circles, which I will draw the pieces here, right? Then I start to connect them with a ribbon here. And I think about these circles as all of them being oriented counterclockwise. Right? So this is my one circle, this is another circle here. Okay. So in the middle, I will draw here 1, 2. Okay. So that was one linking. There will be the second one. And then the third one. Okay. And then I just connect these. Okay. So it's here the linking number. If you think that everything is oriented, huh? So it's everything is oriented here in this fashion.
Пока
And
получилось
the linking number
что на рисунке.
Is
Еще не хватает.
plus 3. Okay.
Пока еще только 2.
3 там, 3.
3.
Each,
Это я побольше нарисую. Wait.
А, да, 3, согласен.
Okay.
Извините, да.
1. And then 2.
each one in a linking
And
number,
then 3.
a pair of intersections.
Yes. And this is, of course, the same as just drawing the picture where I have 1, 2, and 3 edges, each one colored by +1. Okay.
Okay,
We're good?
great.
Okay. Good. So now, now about these numbers. So I explained to you already what to do when you have some weights on edges. So weights on edges do correspond to the weight to this linking number of these two pieces of your ribbon, the way it is linked in the middle. But I didn't tell you so far what to do with these numbers which stand on each vertex. So first of all, I look at this strange matrix, which I called lambda. For simplicity, I just ordered vertices of my graph in any way you like. Okay. It's irrelevant. Just picked up some ordering. So I will look at this matrix, and the only thing which now is interesting for me is what do I do? So I told you what to do on the edge. Nothing. It's on the edge which connects ith and jth vertex. I just keep the same weight. Sorry, it's the same W. But what do I do on the vertex? I had some numbers which stood on these vertices, these D's, and their meaning, I should shift them. Somehow I should compensate for all edges, all outgoing edges. So this process is called, this is known as the Laplacian matrix of the graph. And what I do is I just take the this number which I had on the diagonal, right, which stood for the ith vertex, and I took with negative sign the weights of all edges emanating from this vertex. Okay. Don't ask why, but is the process clear? Huh? What do I do with this number?
I believe it's absolutely clear. Yeah,
Okay.
we see the result on the pictures.
Yeah, so on the picture you see here you had 1, 2, 0, 6. Now out of 1, so I had this 1, but there was also one edge emanating from this vertex with a negative sign. So because I take these edges with the opposite sign, it becomes this 1 becomes 1 plus 1, so 2. Right? here I had 6 on the upper vertex and one emanating edge with a positive sign. So it's 6 minus 1, so it's 5 here. Okay?
Yeah. In particular, the sum of the numbers in each row becomes 0.
Yes, that's what we need. That's the Laplacian matrix. Yeah. If it becomes 0 if these diagonal entries were 0. So if my graph was balanced, then this matrix would have in each row it's and in each it's a symmetric matrix, right?
Yeah,
and in each row it would have the sum of all entries is equal to dii, to the weight of the vertex. So in particular, if the graph is balanced, then all weights sum up in, if you look at them in one row, they sum up to 0.
Okay.
So here's oops, sorry. So another simple example, which was here, I had these weights 3 and 5 on my vertices, but I also had these 2 edges, 2 positive edges connecting them. So it's 3 minus 2 and 5 minus 2. So these weights on vertices are transformed into 1 and 3. Okay. We're good?
Yeah.
So now I interpret the result. This is a certain link, and so there are some numbers which I assigned now to vertices. And these numbers are, I will interpret them as framings of these components.
Значит, вот те числа, которые получаются в результате этой процедуры, написанные на каждой окружности, они рассматриваются как оснащение этой окружности. Мы на самом деле хотим рассмотреть другую окружность, которая наматывается на эту вот с той кратностью, которая там обозначена. Well,
and this agreement about working with this Laplacian matrix, it's just very nice. It's certain technical thing. You will see maybe afterwards. I will try to explain why and how, but so far it doesn't matter. You have a simple algorithm of recreating a link, a framed link from such a planar graph, plane graph. Okay.
mm-hmm.
So now there's a standard topological procedure which is very well known in this manifold topology. It's called surgery on, and in this case it's a surgery on a link. What we do is, given a framed link, we cut out a little tubular neighborhood of each component, and we reglue it back in. The solid torus, which we cut out, we reglue it back in, but in such a way that the former, what was formerly the meridian of this solid torus, is getting glued to a certain parallel now. And to which parallel? Well, this is described by this framing. And so it's certain standard procedure, which is good to know.
Значит, хирургия состоит в том, что мы вырезаем каждую окружность с маленькой окрестностью. Вокруг нее вырезаем такой тор, а потом вклеиваем его обратно, но уже не так, как он был вклеен изначально, а с поворотом вдоль меридиана. Поворот определяется оснащением. В результате мы получаем не то многообразие, с которого мы начинали, а другое многообразие. Это называется хирургия вдоль оснащенного узла.
Да, по-русски это, по-моему, перестройка вдоль оснащенного узла.
Может быть, перестройка вдоль оснащенного узла.
Ничего общего с Горбачевым.
Узлов, которые описываются в зацеплении. Мы делаем это с каждым из них. Хотя узлы тривиальны, но из-за того, что оснащение не тривиально, происходит, каждый из этих узлов нетривиален, оснащение нетривиально, мы получаем другое многообразие. Well,
Да. As an example, for example, just let me do some simple example. Let me switch back in here. For example, if I just take a standard little circle like this, but with a framing which is plus or minus 1, I would get once again the sphere, so nothing will change. However, if I will, instead of plus minus 1 framing, take the 0 framing, so if I would take the same circle but with framing 0, then the resulting manifold will be S2 times S1.
which explains the example in the previous slide.
Yes, which kind of rather immediately give you these examples which we had before. Let me just switch again to full screen, which we had here, this minus 1 and 0. These will be just framings because there are no edges emanating from this vertex. This minus 1 will just result in some small circle, trivial circle with minus 1 framing, and this 0 here on this vertex will give you a small circle with framing 0. So it's well known that the first thing gives you the sphere, as I said, and this one will give you S2 times S1. And it's also equally well known that the Poincare sphere can be obtained just the way I said, by this surgery on this funny link here in the middle. This two-component generalized Hopf link with the linking +2 and 1 and 3 as framings of these two components. Okay.
Great.
Good. All right. Now, so I described for you just one way to switch from this graph to these manifolds, but I didn't tell you anything about how to go back from a manifold to a graph. So it turns out, first of all, that it's possible, and it's non-trivial. It's a non-trivial theorem that any closed-oriented three-manifold can be encoded by such a graph. I will maybe tell you a few words about that. I don't know how we're doing with time. Not very good. So maybe I'll just move, and then in the end, if I'll have time, I'll explain. But it's possible. And not only that, but you can also do it if your manifold is given in many different ways. So, for example, if you start just from any surgery, not on such link, but any other link, if you're given a Higard decomposition of this three manifold, or if you're given what is known as plumbing, or if your manifold is given as a double cover of the sphere branched along a link. So there are several options in there, but it can be done. I will not enter details, but believe me, it's not very complicated. Okay. So what I just want to say is that I explained this construction for an object which was just a bare manifold, just a closed-oriented manifold, but it can work also with in some generality, for example, for links and three manifolds, or if your three manifold is endowed with some spin or spin C structure, or if you want if it's not a closed manifold, but it's some mapping cylinder where you twist some surface by some elements of the mapping class group, right? And this can be done as well. So I will not explain it very much. I just will indicate you how to do that. For example, if I want to give you a knot, a trefoil knot in a sphere, so what I do is I just mark specifically some vertex of my graph. Okay, so this vertex will be special in my construction now. And actually what I will do is I will, starting from this graph here with this marked vertex, I will construct a link as before, exactly the same way as before. But what I'll do is I will do surgery on all components of this link, except for this marked component. Okay. We're good? For example, this graph will result, as I explained before, in some Hopf link, kind of generalized Hopf link with two components. Before I did surgery on both components. Now I just hold tight my first component and I don't do anything in there. And I consider it as a knot in the 3 sphere, but I do surgery on the second component with this weight 3. So I get, it turns out that what I will get, it will be, the manifold will still be the same sphere, but my component, my knot, which was before totally trivial, will now become non-trivial. And it will turn out into a trefoil knot. And I just gave you 2 examples so that you will see that it's non-unique. You can just translate it back into the setup which I explained before and see that it works. Whoever knows how to do surgery will recognize trefoil in the sphere.
То есть, если ты выделяешь какую-то компоненту, по которой не делаешь хирургии, да, а все остальное делается так же.
Да, все остальное делаю так же. Я получаю какое-то новое многообразие с каким-то узлом, живущим в нем.
Ну, или зацеплением, если...
Если я... Нет, зацепление будет, если я отмечу несколько вершин. Если я отмечаю только одну вершину, это обязательно получится узел. Просто он может быть нетривиален, и он может жить в нетривиальном многообразии.
Окей. Clear.
Okay, good.
Это...
All right, so I will not explain more, but I just left it if you want me to draw something here, but if we are good, I'll move further. So what I already just have shown you before in some picture is that such an encoding of a manifold by such a graph is not unique. However, the beautiful thing is that there's a finite set of some simple moves which allow one to pass from one encoding to another. So the theorem is that if a manifold is presented by 2 different chainmail graphs, then there's a certain finite sequence of some simple moves which allow me to move from one to another. I will not show you all moves because I have some long list. My conjecture is that I can get rid of almost all of them, and I just drew up the ones which are indeed important. So conjecturally, I can just manage with these ones, and also cutting off a dead leaf, what is called, cutting a dead branch, whatever they say. But these are the main moves. And
Sorry, a question right now for the picture. Are these moves invertible?
Yes. So when I just I'm not very good when I prepare these presentations. I do the minimal work. So I drew here some arrow in one direction, but it should be in both. So you can invert. It's like with Reidemeister moves. I just consider them in both directions, here and there. So so it's a nice thing. It's a nice set of moves, actually. There are a few more which I conjecturally can get rid of, but it's complicated. It's the whole bloody story. It's long. I will not tell you everything, but why did I draw these three and not the others? First of all, because conjecturally I can manage with these, but secondly, because these moves are extremely interesting, and I'll explain why. So this move in the middle is very well known in, for example, in electric networks. This is the celebrated star triangle thing, right? Or whatever, delta star move or something.
Delta Y move.
Delta
Yeah.
Y move, yes. I don't call it Y because I have it oriented and upside down, but it is, yeah. So all of these. There is also, so if you will notice, I only drew it here for this epsilon, where by epsilon I mean plus or minus 1.
Plus or minus.
So there's the question, why did I do that? Yes, and you see there's nothing near the vertex, which means that in this central vertex, I assume that the weight is 0, that it's balanced. And if you know electric networks, you should even understand why. But in fact, I can also do, so you can ask me, can you do that for, say, when all three of these weights are plus 1s? And yes, you can. There's a certain version of it, but I don't want to get into it. I drew just these specifically because they're extremely important, and they appear not only in these electric networks, but they correspond to many beautiful things. So first of all, if you think about it, maybe let me remove it so far. So so what's the first move in here if you think about it in terms of this surgery? Well, it turns out that this is one of the standard Kirby moves. And this in the middle is also one of the standard Kirby moves. And that on the right is also one of the standard Kirby moves.
But there are only 2 standard Kirby moves. And there are 3.
It depends. There are different ways. No, there are not 2. If you think about what? Handel slide, a general one?
Yeah.
No, I don't like this one because it's a global thing, right? You have to slide a handle along some huge knot. I want to do it local, and I want to keep it in the simplest case when I work with these unknotted components which are linked in between themselves in some simple fashion. So first of all, I would like only to work with these, not actually with Kirby moves, but these Fenn-Rulke moves. And Fenn-Rulke moves I would like to do only if, you know, there's one component when it goes around at most 3 others. It's known that it generates. So there's one component which goes around either 2 or 3, 1, 2, 3 other. Okay.
In the third move, can we replace plus by minus?
No, like 2 plus and 1 minus.
Yes, but then, yes, you will just get minus, 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 and it will be minus, minus, minus.
Yeah,
Totally symmetric.
Okay.
So, so the kind of, but the beauty of this, so if you look at these moves, you should recognize at least some of these Kirby moves. If you thought about the way I described for you these the way to construct the surgery link from this graph. And I gave here an example of how does it look on this, how does this move look, but just in the opposite direction, in fact, here. So my left graph, right here, is just this move. And it's known that it's a kind of, this is a correct move if the circle in the middle is 0 frame. And this is the other move, and it's a version of this Feynman move when there's one kind of standard circle which has the framing +1, and it goes around, around 3 components here, which are, so let me maybe just a second. Let me maybe draw it fast for you. It's actually a version of the following move. 1, 2, 3, and then a circle around. Okay. And then if that was a +1 framing, then this goes into the negative twist of these 3. Okay, so something like this. Right? And the framings are changed by -1. So all framings also are dropped by 1. But if you would just think about this picture, which I had before, oops, sorry, let's go back to these pictures before here. So this is more or less what I drew in some other way. Any questions on that?
No, thanks.
Okay. But an amazing thing that the same graphs already appeared before, and the same set of moves appeared before, and it was not for 3 manifolds, and no, they did not correspond to Kirby moves, and they had not much to do also with this electra statics in general, but these were just Rademeister moves. And they appeared in the following way. There's a standard construction. So let me just explain you how does it work for the second Rademeister move. So let's take a little piece of a node diagram or link diagram, okay, and perform a Rademeister move 2.
Yeah.
Now I will just color all regions of this diagram in black-white colors, right, in the chess type coloring, so that neighboring regions have opposite colors, either blue or black or white. So these 2 here are white, this one in the middle is black. So coloring of the first diagram gives you automatically the same coloring of the second diagram, and vice versa. Okay.
Yeah.
Now the graph about which I was talking before would be a graph where a vertex would stand for each black region, and 2 vertices will be connected by an edge if these 2 regions are connected by a crossing, and this edge will have a sign. It will be either +1 or -1, depending on the sign of this crossing. Okay.
Yeah.
So
But
that's why the picture on the left, this one, this graph, this is the same as I drew here for R2. There's plus and minus on these 2 edges. Okay.
Yeah.
And this graph in the middle, this delta y or star triangle transform on this language corresponded before to just the Reidemeister 3 move. And again, signs on these edges would be plus, plus, minus, or minus, minus, plus, just as it should be. Okay?
Yeah.
So an amazing thing, which I myself, I don't know why it happens. Have no explanation for that.
Looks
But
like
except that simple thing happen all over again in many fields. But this set of moves, kind of Kirby moves in this language, are related to these Kirchhoff moves of electric networks. They are also related to Reidemeister moves on links. Why does it all happen? Have no idea. But it's a funny thing. All right.
Mhm.
Okay. Good.
Good.
All right. So now, if so, then let's move further. So I just explained for you this encoding of these manifolds.
Misha, could you explain? Is it just mnemonic rule, or there is some direct correspondence between
Нет, это странное совпадение.
interpretations of the book?
What? Sorry. What?
Максим, тебя плохо, Максим, тебя плохо слышно. Ты не можешь микрофон какой-нибудь взять?
У меня вопрос такой. Эти движения связаны только формальным таким мнемоническим правилом, или там есть какое-то прямое соответствие? Можно там сопоставить многообразию линк и так далее.
Там есть какая-то хитрая штука, которая, значит, я могу через какие-то разветвленные накрытия объяснить это как-то, немножко размахивая руками. Но на самом деле я не понимаю это философски, и почему это все происходит, для меня некая загадка. Ну, кроме того, как, знаете, вот почему всегда появляются деревья и подсчет деревьев. Ну, потому что вот это такой простейший объект, и он всегда появляется. Да? Так что, может быть, и тут это та же причина. Может быть, есть какая-то глубокая, и я ее не понимаю. Это для меня было некой неожиданностью, и я ужасно обрадовался и прыгал вокруг, и довольно долго пытался ее как-то почувствовать руками и понять, и ничего не смог. То есть я реально могу это объяснить через какую-то, значит, вот, если у меня есть движение Reidemeister, давайте теперь сделаем какое-то там трехмногообразие через разветвленные накрытия, бла-бла-бла, там какая-то джопа. И все это, в общем, как-то это все видно через какую-то жопу, не знаю.
Понятно, спасибо.
У вас студенты знают слово жопа?
Ну, это такой
Хорошо. Okay, good. So, so now the funny thing. So this was actually the first funny thing. Which I did not say before. If I would start from another encoding of a 3 manifold, for example, if I would look at Higger diagrams, right? So I will think about the group of diffeomorphism of the surface, right? The mapping class group. So then this star triangle relation will be, I did not explain you how I construct the graph starting from a word and these generators of the mapping class group, but with standard generators of the mapping class group, this relation would be something like alpha beta alpha equals beta alpha beta, which is kind of the relation in the mapping class group. So why does it happen? It's really, it's a beautiful thing, which I absolutely do not understand. And I'll be happy to discuss it afterwards, but probably not now. Okay. So let me go for interesting things now. So what I want is, so you have a seminar in some invariant. So let's switch to invariant. That was the purpose, actually. So, all right, so we got some encoding of 3 manifolds by graphs. And I would like to think about some invariants which I can produce starting from this graph. Can I possibly produce from a manifold, I go to a graph. Graph is a purely combinatorial object. And for example, if I look at this matrix, which I defined, this matrix of these weights, can I possibly look at it and produce an invariant? So the obvious question is, let's try to look at this determinant of my Laplacian matrix. Okay. It turns out that it is invariant, and it has a kind of, it encodes the best and simplest homological information about my 3 manifold. Namely, the determinant is non-zero if and only if M is a rational homology sphere. So it detects whether your manifold is a homology sphere. Now, if it is a rational homology sphere, so you have the torsion, right? So you have the size of H1 of M. So if it's an integer homology sphere, it's just 1, right? But if it's a rational homology sphere, it could be 24 or 7, whatever, 5. So this determinant up to a sign just measures for you the torsion.
And what about the characteristic polynomial of this matrix? I've asked you about.
I know, that's the question I expected from you, of course, because you always ask about characteristic polynomial. So this we should discuss afterwards. It's interesting. Okay. I will not, you know, when I don't know something precisely, or I don't want to tell people something, I was told and I was taught by some people to say that it's an excellent question. So it was an excellent question, and we should actually discuss it afterwards. But after that, it turns out that you can recover a lot of interesting things just looking at some simple polynomials which are very similar to the determinant in a funny way. So how do you do it? Let's just to see how would we. So suppose that you trust me and that it actually gives you this determinant of this matrix gives you H1. Yeah, you can get this if you know, for example, this Sturgery calculus. Well, you should know what happened. But anyway, suppose now that we do know that. Can I somehow see it and feel it diagrammatically in a graphical way by some graphical calculus from my graph itself? You know, not looking at the matrix, but just looking at the graph. So the determinant of this matrix, this one, is actually it's a count of cycles in your graph which pass through each vertex. These are oriented cycles. So you pick up one of the orientations. Each cycle should be oriented. It's a collection of edges, and you draw several such, with the only rule that that these cycles, this collection, will enter and then leave each vertex exactly once. Now, it may include looped edges because these looped edges have to do with this disbalance at a vertex. Kind of, I can work with this in terms of little looped edges. I can interpret this defect in each vertex by drawing some little looped edges for this way. Okay? This I don't want to do, but it may include this. But so if I have such a collection of cycles, then I just count them with the following coefficient. First of all, I should know how many cycles are in there. So n is the number of my vertices, k is the number of cycles. So just insert a certain sign, and then I go over all, and then I go over all edges which I have in my picture, and each edge I count with this number, which is L of E. Now, I wrote here this L of E and not W, because if these are edges which connect two different edges, it's just the usual weight of the edge. But if it stands on the diagonal, then it's this specific kind of number which we assign to a vertex, right? Okay. Now, so that means that we can at least produce some simple invariant, kind of the very basic one of our manifold by just counting with certain weights, right? And we see how it works. We count these subgraphs, which look like collection of cycles. We count them with products which up to a sign correspond to these products of these edges, weights on edges. But now, so the idea would be just to consider more complicated subgraphs. So instead of just a collection of loops, let's go up and consider more complicated ones. So that's what I would do. Okay. And kind of the conjecture about the next invariant is very obvious.
Я правильно понимаю, что доказывать, что то, что предъявляется, является инвариантом, для этого нужно проверить, что оно сохраняется при всех вот этих движениях.
Ну, есть два пути, да? Есть честный путь, и это проверить, что оно сохраняется при всех движениях. Есть нечестный путь. Например, если ты уже знаешь, что какое-то число или что-то там, это инвариант, ты можешь его посчитать на одном из графов и сказать, а вот это мне дает вот таким-то там хитрым путем, я могу его идентифицировать, например, какими-то его свойствами. Да, я могу думать о его свойствах, там, что с ним происходит, если я меняю мой граф неким простейшим образом. Если я в нем стяну ребро, или если я в нем что-то разорву ребро, да? Или если я изменю вес вершины на единичку, что произойдет с моим подсчетом? И окажется, что при таких движениях, например, число, которое я считаю, вот этот подсчет подграфов, изменяется неким контролируемым приятным образом. И тогда я его идентифицирую, потому что я скажу, а вот мне там типа большие люди сказали, что инвариант Кассона-Уокера-Лескоп ведет себя так-то при каких-то там изменениях моего многообразия. А тут типа смотрите, для простейших многообразий я знаю, как он себя ведет, я могу его посчитать, и я вижу, как он меняется при каких-то движениях. Все, привет.
Да.
Это жульнический способ, но это, к сожалению, тот, которым я пользуюсь. Поэтому все мои рассуждения про более там какие-то хитрые инварианты очень высоких порядков, они до сих пор у меня сидят как гипотезы, а не теоремы. Потому что я проверить руками инвариантность при всех этих движениях просто не могу. У меня не получается. Это надо, ну, надо кого-то умного, типа студента, да, который умеет сесть там, что-то считать. А я, куда я уже гожусь, да, я не могу, мне лень. Вот.
А тогда есть два связанных вопроса. Один вопрос такой, что вот предъявлен некоторый список движений. Верно ли, что проверить о том, что один взвешенный граф и другой взвешенный граф соединены цепочками движений, это алгоритмически разрешимая задача? И основной вопрос, верно ли, что если два многообразия изоморфны, то тогда любые два его представления в виде графов связаны цепочками этих движений?
Ну да, вот я уже сказал, есть некоторый набор, конечный набор достаточно простых движений, который я знаю, про который я знаю, что он полный, то есть конечной последовательностью таких движений можно точно перейти. Я не знаю, минимален ли этот набор, и, по-видимому, от многих движений можно отказаться. Проблема в том, что у меня их сейчас пока просто слишком много, они большинство дурацкие. Это какая-то штука, с которой я уверен, что можно справиться, они у меня по техническим причинам появляются. Но
я просто
но они мне мешают.
Отсюда не вытекает ли какое-нибудь комбинаторное доказательство теорем Пуанкаре, гипотезы Пуанкаре? Если так все просто, если все трехмерные многообразия можно так просто кодировать, может быть, все их можно перебрать и гипотезу Пуанкаре отсюда получить.
Ну а как? Понимаешь, ну это как с хирургией, да? Вот мы знаем, что все замкнуто ориентируемые многообразия получаются хирургией по оснащенным зацеплениям. Мы также знаем движение Керби. Движение Керби можно превратить в локальные движения, в конечный набор локальных движений. Ну а как это тебе помогает? Вот как этим путем ты можешь доказать? Ну вот то же самое, да, это некая проблема.
Понятно.
Окей, let's proceed.
Okay.
Okay, so the idea would be is to look at something which kind of was already known from this Chern-Simons theory, and to look at Feynman graphs which appear there, and to hope to construct invariants in the following way. When you look at these vertices of a Feynman graph before, in this configuration space integrals, they gave you a configuration of n points in your manifold. Now you should just look at the set of n vertices in your graph. And instead of these propagators, which connected pairs of these points in M, you just look at some path connecting these two vertices, which connect them by edges of your graph. Okay, so that would be the idea. And integration over the configuration space should boil down to the sum over subgraphs. So that's the intuition. Now, how does this work? Yes. So there are these complications in the Chern-Simons where you have all these compactifications blow up and some anomalies where some points in your manifolds start to collide together. So here you would just look at when you count subgraphs, you should look also at some degenerate graphs when several vertices merge together, okay? And some path of edges collapses. So that's just ideology, but let me explain how it's done for the next non-trivial invariant, which is already quite complicated. So the next one is so-called the theta graph invariant. It's some version up to normalization. There's a lot of papers by Christine Liskop where she identifies it precisely with some version of the Carson-Walker invariant. Actually, there was a preprint by Dylan Thurston and somebody. Sorry for that. Whatever. Many years ago, it was never published. The idea is there, but some proofs are missing. But it turns out that in some way, this theta graph count via configuration space integrals correspond to up to a certain normalization to Carson-Walker invariant. So now, what I would then expect? I would expect that I just now look at such theta shape graph. By technical reasons, it means that I already order its vertices, and I also distinguish these three edges. Okay, so I really order them 1, 2, 3. And I count the number of embeddings, if you wish, of this simplest theta graph into the graph, my chainmail graph, which encodes my manifold. And I should count these maps with certain weights and multiplicities, which multiplicities correspond to some symmetries. Okay, so so what does it mean that I look at such maps? Well, first of all, I should say that these vertices 1 and 2 of my theta graph should go into some vertices of my graph G, right? So I should pick up a pair of vertices of G, and then 3 edges should go into some collection of edges. So here first, on my chainmail graph, which encodes my manifold, I should fix such a pair of vertices, and then I should look at a triple of paths in it. Okay, so here's the first path, 1. Okay. So this is the second, 2, and this is the third. Okay.
Probably it would be better if the passes would be of different color.
It would be, but it's not going to happen. So, sorry, but you can distinguish your 2 special vertices, these ones, right? You can distinguish them now in this picture because these are 3-valent ones. The rest are 2-valent now. See that?
Миш, слушай, у нас через 15 минут другой семинар.
Уже другой. Ну вот, я, собственно, все сказал. Давай я быстро пробегу еще несколько и все. 3 минуты. Давай. Вот. Now, the weight of such an embedding is what? So first of all, I look at products of these weights on all edges which enter the subgraph. And then I look and I multiply it by something which corresponds to the leftover part. Should remember some minimal data about the leftover. So I look at all the leftover part of my graph, and I look at this minor of this matrix corresponding to leftover vertices, to the complement vertex. Okay? Good?
Yeah.
So it turns out that I also should, as I said, count some degenerate maps. So my, you see, I had the theta graph, but it could happen that on this theta graph, one of the 3 edges collapsed into a point. So then it becomes this just figure-8 graph. And I should also count such mappings of these figure-8, okay, with some multiplicity. So, and I should count even more degenerate ones when one of the lobes of this figure-8 sits in one vertex. Okay, so these are more and more degenerate pictures, embeddings. So it turns out that what happens here is that if I count them correctly with these weights and multiplicities, then the sum over all such embeddings is an invariant of my 3 manifold. And if it's just a rational homology sphere, so this determinant is not 0, then I get up to renormalization this Kassan-Walker invariant. It's slightly shifted by the signature and by multiplication by this size of distortion, but it's basically there's this Kassan-Walker, as expected in some sense.
Yeah.
Okay, so oops, sorry, where am I?
You consider, Misha,
Okay.
You consider the theta graph with exactly the weights you have shown, yeah?
Yes. So a conjecture already for the next one, it's not very easy, but a conjecture that the next perturbative invariant can be obtained in a totally similar way, counting maps of the next expected Feynman graphs, which are these two.
These are graphs with 4 vertices rather than 2.
Yes. They're all trivalent, right?
Mhm.
Trivalent graphs by some simple combinatorial reason could only have an even number of vertices, right? So after 2, you immediately see 4. Nature tells you that. So a funny thing is that when you look at these expressions, let's say for the theta graph, and you think about this as you look at it and you think about it as how does it depend on the entries of your matrix of this matrix? Well, it's just a polynomial. So before you had determinant, but now it's a polynomial of the next degree, of the degree n plus 1.
Mhm. Of the next degree, yeah?
And yes, for the next degree. And then there's a nice conjecture about finite type invariant of 3 manifolds in general, which I will not talk about because I don't have time. And then I will go with that and say that instead of counting embeddings of this theta graph into my chainmail graph, we can just count the theta subgraph if we count them correctly with multiplicities. Additionally, because we need to count for symmetries. It's just easier to see the number. You see, before I mapped, and I had these 3 of my edges were different, right? They were ordered 1, 2, 3. So now I look at subgraphs, and each edge here, it could be 1, or it could be 2, or it could be 3, or it could be the opposite. So there are totally 12 such possibilities, right? Because also this vertex could be 1, and this could be 2. So there's 6 times 2, a total of 12 mappings which correspond to this subgraph. So you just count symmetry.
Yeah.
And then that's the way you count. And then here's an example for the Poincare homology sphere below. And I just I computed it for you, and you can afterwards look at that because now there's no time, but to see how exactly do I count with these coefficients which I told you about, and you get 24 as your theta invariant, which is exactly what you should do. 24 is an expected answer. So that's more or less, okay, blah, blah. Yes, and then there's the whole story about an expression for this theta invariant. Instead of kind of counting with my Laplacian matrix, I can also count it with the regional weight matrix. And that's a version of some matrix 3 theorem about which I will not talk, but it means that I will now count not embeddings of my theta graph into my chainmail graph. But now I will look at spanning trees, but which are based on a cycle, right? So they are rooted on a cycle. There's an oriented cycle, and then this collection of edges all going down to this cycle in there. And it's some kind of generalization of a funny matrix tree theorem, which tells you before, kind of the standard one tells you that the determinant can be counted in some way as, or rather minor could be counted in the Laplacian matrix by counting correctly rooted trees. And here it's the next polynomial of the next degree, right? It's already not just, you're not counting cycles in the beginning, you're counting theta graph also. So it corresponds also to some kind of counting trees, but now they are rooted not in a vertex, but on a cycle. Okay. So it's kind of a beautiful thing in itself.
Yeah.
Euro Burman likes it a lot, and he wrote about it afterwards. When I told him this, yeah, he wrote already, I don't know how many papers around it. So even this piece you can do and enjoy it also separately. Okay, that's it. Maybe I will just stop here because that's okay. It's something else. I was going to talk also about why this is counting orbits of vector fields, closed orbits of vector fields, and it does not matter. So this can be interpreted as counting closed orbits of some discrete vector fields, blah blah. And then I was going for Gopokomar Wafa, but of course I will not do anything. Okay. All right, I'm done.
Okay, thanks a lot for a very clear and
Да,
inspiring.
где-то я раньше это встречал, а это называлось вариант весовые системы имени Веро и Поляка. Но там комбинаторика была, конечно, попроще.
Да. Может быть, я еще должен вот что сказать. Давайте я уже сейчас скажу, что вот, значит, я сейчас специально говорил про трехмерное многообразие, просто потому что мне было лень вообще писать новые самые презентацию для чего-то еще. Значит, у нас в совместной работе с Яшей Мостовым мы решили, значит, мне просто надо было технически, так как я работаю вот с графами, и потом перехожу от них к зацеплениям, да, а потом делаю по ним перестройки, мне надо было, значит, вот я смотрю на зацепления очень специального типа, да, здесь, вот эти кольчужные зацепления. Мне надо было что-то там про них говорить. Из этого выросла некоторая работа про новое кодирование зацеплений и узлов. Они кодируются какими-то такими смешными игрушками типа хордовых диаграмм. Там действительно хорды, они не направленные, там нету никакой науки про виртуальные узлы, там теорема про универсальный инвариант делается сразу, и все это очень приятненько вообще. И если кто-то хочет, то может посмотреть на наш препринт с Яшей. Мы его не апдатировали, там у нас сейчас стало существенно больше всего и симпатичнее, но хотя бы тот уже хорош. Вот, он просто чисто про узлы, как считать инварианты Васильева, подсчитывая подграфы, которые считаются в каком-то другом таком простом графе, и прям там видны хордовые диаграммы, и все очень миленько. И это как бы не Поляк-Веро, это некоторая другая технология, но в принципе, если вы хотите, можно считать, что вот здесь для трехмерных многообразий это некая версия такого комбинаторики типа Поляка-Веро, и подсчет такой же. Вот диаграмма очень похожа. Все.
Хорошо, спасибо.
А вопрос можно? А почему просто в духе вот вашей работы с Яшей Мостовым не сделать то же самое? То есть из графа сделать сумму по всем подграфам и дальше посмотреть, как эти движения на этом пространстве выглядят. И смотреть, соответственно.
Нет, ну сейчас, а как производить сейчас, если что, если делать многообразие, извините, если делать инварианты чего? Зацепления или многообразия?
Ну, граф, значит, оперирует многообразие.
Да.
Значит, дальше. Операция, которая графу составляет сумму по всему подграфу, это изоморфизм на верхнем пространстве графа.
Да.
Соответственно, как бы у вас яшкой сделано как, что вы берете, значит, вот эту версию пространства графов, ну и просто смотрите, какие функционалы на этом пространстве зануляются на подпространстве параллельным соотношениями.
Да, да.
Ну и вот здесь просто как бы напрашивает тот же самый подход.
Ну, конечно, я просто не знаю. Значит, дело в том, что у меня сейчас в данный момент, как я уже сказал, довольно много движений здесь. Если брать сумму подграфа, я, конечно, могу сформулировать теорему и про инварианты, и вот, но я ничего не могу сказать, сколько их, покрывают ли они все инварианты конечного типа трехмерных многообразий, что там с ними делается. У меня есть прикольная новая формулировка теории инвариантов конечного типа для трехмерных многообразий, потому что раньше это было очень уродливо, и вообще из-за этого мало кто занимался инвариантами Васильева для многообразий. Вот через это кодирование есть некоторое смешное новое определение инвариантов конечного типа, ну и с ними надо работать, там надо что-то делать. Да. Я просто совсем не успел ничего, да, потому что вот мы с Яшей уже, мне надо было как один технический шаг, чтобы работать с многообразиями, надо было хотя бы победить все движения, получить хороший маленький набор движений хотя бы для разных кодирований узлов, уже и зацеплений. Ну, оказывается, что это уже заняло 4 года, да? Так что я там где-то копаюсь, там свой садик дальше поливаю. Там, да.
Я прошу прощения, нам все-таки надо переходить к следующему семинару.
Вперед!